Okay, so the last type of bond we want to talk about are hydrogen bonds. Okay, so let's review a little bit. Ionic bonds. Electrons given and received, making an anion, negatively charged ion, and a cation, positively charged ion. If one is negative and one is positive, they are attracted. Okay? With covalent bonds, electrons are shared. If those electrons are equally shared, we don't have an area that's a little negative and an area that's a little positive, so we call those non-polar covalent bonds. But if there's a difference in electronegativity, those electrons spend a little bit more time on one side than the other, then we form a polar covalent bond. So we have non-polar covalent bonds and we have polar covalent bonds. So the last we want to talk about hydrogen bonds. Okay, now if you look at the diagram in your slides, you'll notice here I have a molecule of water. Actually, I have 4 of them. 1, 2, 3, 5. Can't count. I have 5 of them. Okay, so I have 5 water molecules. And the water molecule consists of an oxygen, very high and right on the periodic table, very electronegative. Hydrogens are less so. So they form covalent bonds. But there's not an equal sharing going on here. So those electrons are going to spend more time by the very electronegative oxygen and less time by the less electronegative hydrogens. So that makes this area of that molecule a little bit negative. That makes this area of the molecule a little bit positive. So are these ions? No. We don't have big pluses and big minuses, but we have a little bit negative and a little bit positive. So would there be an attraction to other molecules that are positive or negative, or a little bit positive and a little bit negative? There are. And there are weak attractions because it's a weak charge. So couldn't we then look at this and say, all right, I have another water molecule, so wouldn't the little bit negative of this molecule have a weak attraction with the little bit positive of this one? Or the little bit positive of this side having a weak attraction with the little bit negative of this side? Or the little bit negative with the little bit positive, the little bit positive with the little bit negative? You kind of get where I'm going with this. So let me summarize it this way. Well, let's go to the next group, and then I'm going to summarize it. That hopefully makes it a little bit easier. Okay. So because the water molecule forms polar covalent bonds, making this side a little bit negative and this side a little bit positive, it then creates the opportunity for it to form hydrogen bonds. Okay, so let me state it this way. I'm going to go back 2 slides, and then I'm going to go look at some other examples. Okay, here's the way you want to think about it. Hydrogen bonds between molecules form due to polar covalent bonds within molecules. Okay, so look at the diagram. Hydrogen bonds form between molecules because, or due to, polar covalent bonds forming within molecules. So the polar covalent bonds formed within the water molecule that created the opportunity for the hydrogen bonds to form between molecules. Now, is this important? This is so way important to basically life as we know it. And you're like, really? Okay. Actually, yes. Okay. So basically what can happen, so what this is common whenever we have an oxygen and a nitrogen, okay, forming bonds with like carbon, and then having the opportunity to form hydrogen bonds with these hydrogens. Okay? So notice here I have an oxygen, very electronegative, forming bond with carbon, making this part a little bit positive, this part a little bit negative. Then it comes into contact with another molecule that has electronegative nitrogen with hydrogen, a little bit negative, a little bit positive. So now the plus will be weakly attracted to the minus, so they can form a weaker hydrogen bond. Same thing is true here, same thing is true here. So we're still forming weak hydrogen bonds between hydrogen and like nitrogen, oxygen, those electronegative atoms. And this becomes important because this is where I can get bonds to form, but I can also break these bonds as well. And so they're easy to form, but they're also easy to break. So things that I kind of need to open up, okay, it's kind of like having storage in your house where you got the special little totes that you stack up a mile high because you don't want to ever throw away anything, okay, and you keep certain ones really close and they have lids that are easy to open so you can get in, get out, okay. Those hydrogen bonds are really going to help us in that regard in our body, where if there's things we need to basically pull apart but then quickly put back together. So if we look at these kind of relative bond strengths, now this is just in general, okay, there is never hard and fast rules when it comes to science to say, well, a triple covalent is always stronger than a double, and this double is always strong. No, it's not actually not the case. But in general, our strongest bonds, and this should make sense because you can use a relationship analogy here. When we have two individuals who equally share things, they tend to have a strong attraction to each other. When we have someone who completely is the giver of the relationship and completely is a taker, yeah, okay, or one that's just little bit likes the other one and the other one little bit likes the other one, well, that's not a very strong attraction either. So we can kind of use a relationship analogy here, okay? But our bond strengths in general, triple covalent bonds would be the strongest, followed by double, followed by single, our ionic bonds, but of course our hydrogen bonds would be the weakest. And in our body, we utilize these different types of bonds. So with carbon dioxide, it's a compound that has very strong double covalent bonds. Sodium chloride, weaker, we can break it with water, okay, is our weaker ionic bonds that we can break apart. So some of the other examples are gases that are dissolved in our blood, okay, our covalent bonds, because we actually carry oxygen in our body as an oxygen molecule, not as an oxygen atom. So we carry it on our protein in our red cells that carries oxygen for us. You know it as hemoglobin. We carry it as an oxygen molecule, so as O2. We also have nitrogen as a nitrogen molecule and CO2, okay, as a molecule. When we form proteins, we don't want them to fall apart once we put them together. And so therefore, when we first make them, we hook them together with covalent bonds. Our DNA and our RNA, if you look at the strands of those molecules, they're held together by covalent bonds. Now, DNA, and you've seen the DNA molecule, because everybody in elementary school and junior high has to put one together. You'll notice that you had to make it look like a ladder. The sugar molecules and the phosphate molecules that form the sides of the ladder are covalent bonds. The connections between the sides of the ladder are hydrogen bonds, because we don't want the DNA to fall apart, but we have to open and close it to kind of use the instructions that are there for us. Okay, our ionic bonds, our teeth and our bones, okay, also our dissolved ions as our electrolytes. Our hydrogen bonds are going to hold our protein structure together. Now, they didn't form, it's kind of like we hook up the amino acids to make a protein, and we hook those up with covalent bonds, but then it starts to twist and turn and coil and fold and do other things, and hydrogen bonds play a role in that process. And then I mentioned the fact that we hold the DNA together, the two strands together, with hydrogen bonds. So these are very important to us.